Okay, so today we are going to talk more seriously about using R as a programming language, right? So we've talked about using R for statistics quite a lot and how to do various kinds of math operations, but R is also a fully featured programming language and has a lot of tools that feature in other programming languages. So obviously this is a really rich and deep topic. We're going to cover kind of two of the most commonly used tools for kind of advanced programming tasks. That's loops and functions. So um, today, I go ahead and make sure you have pulled or fetched the latest updates to the Git repository because there's a script in there that I'm going to ask you to run in a little bit. So if you haven't done so now, go ahead and fetch. And this one is going to be, one where I do want you to have RStudio open and writing code with me as we go. This is going to be an introduction to some concepts that are, if you haven't seen them before, will be foreign and will take you some time to master, but they will take your programming up to the next level, right? And they'll make you. It'll take a lot of practice, but once you get good at this stuff, it'll make you a lot more efficient in terms of your code. And if doing applied data analysis is something you could see yourself doing in the future, then learning this kind of stuff is really critical. Um, One piece of advice, if you want more on R as a programming language, then the two things that I would strongly advise. So in the syllabus, I link to Hadley Wickham's R for Data Science. That's a great textbook to walk you through the kind of theory. It's written for the tidyverse, but it's really got a lot of kind of computer science theory for how to think about using R as a programming language. Also, Jenny Bryan's Stat 545 class, which is also linked in the syllabus, is another good place to go for more on this. We're kind of giving you some snapshots of this stuff in lab, but if you want really to build your skills up, those are two good places to go next. There's a lot of resources on kind of more advanced R, but those are two really good ones. Okay, so loops. What loops do is they iteratively execute some set of commands, right? So iteration means doing the same thing over and over again, right? And that's exactly what a loop does. This is just about the simplest loop I could write. What I'm doing is I'm going to define some variable I. And what I'm going to do is I'm going to allow I to exist in the range 1 to 10. And what's going to happen is whatever's inside the bracket is going to execute. And each time it executes, I will increase by 1. It'll go to the next value in that sequence. So I will start when it goes as value 1. Then it will execute the command here. First, it'll print hello world, and then it'll print I. The reason I have to use print here is to get R to spit output to the console. I have to tell it explicitly inside of a loop. I have to tell it to print. Usually, we don't need to use that function. But here it's going to say hello world, and then it's going to say 1. And then it hits the end of the code block, right? And it hits the closed bracket. And so that means it knows it's the end of the loop. And what it's going to do is it's going to go here, and it's going to say, okay, we're done with 1. Now, what 1 to 10, right, is a vector of values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the next value is going to be 2. I will now be set equal to 2. That's going to say hello world 2. Then it's going to do it again. Hello world 3, etc. Right? And it's going to go all the way up to 10. And then when it hits 10, this block of code is done, and it's going to move on to whatever next I have in my script. Right? So a loop is a way for us to run the same set of commands multiple times, but potentially with varying values. Right? And so it's a way for us to iterate over something. Right? And that, is kind of generically the broadest definition possible. We can get really creative with our index, right? So here I've said I is 1 to 10, but I could be for I in and then make a vector A, B, C, right? And then for the first run, it would be A for the first, second run, it will be B for the third run, it would be C. The index typically, I think you'll want to keep it relatively simple, like using integers 1 to 10, but you're not restricted to doing that. Okay, so there's no reason we can't put loops inside of loops, right? And this is one of the more kind of useful applications, right? So this is called a nested loop. Here we have two indices. We have for I in 1 to 3, but then on top of that we have for j in 1 to 2. So how many total iterations are we going to get on this?
6.
6. We're going to get I times, we're going to get, the length of j times the length of I numbers of iterations, right? Because what it's going to do, it's going to start out, j is equal to 1. Okay, now j is equal to 1. For I in 1 to 3, go I is equal to 1, j is equal to 1. I is equal to 2, j is equal to 1. I is equal to 3, j is equal to 1. Right, so it's going to execute the full run of that nested loop for every j index, right? After it's executed I equals 1, 2, 3, then it will move on to j equals 2, right? So we'll get j now to I is 1, 2, 3 again. So I'm going to have us work some examples here, but a common application for this sort of thing that I've used in my work is when I need to run some complex math operations over subgroups, right? So for example, the fatal encounters data we used, right? I used this kind of nested loop structure to run what's called a life table estimate over sex and race specific subgroups for various years. So I had a year loop, I had a race loop, and I had a sex loop, right? And so for each sex, for each race, and for each year, I would get one table, right? Which I could then store in a list and use later. But in that case, I had 3 levels of nesting, right? And I would get years times race times sex number of tables out of that, which ended up being a few hundred, right? But we can use this in really kind of sophisticated ways to make complex operations a lot easier. So I want you to practice this. I want you to set up a vector named x with length 10, where each value is a random numeric variable. And then we're going to use a loop and matrix indexing to create a new vector called y, where each value y is equal to 2xi. Okay, so I'm going to copy those over into my R environment. I've just created a new script called Scratch that I'm going to use for practice here. Okay, so 1. Set up a new vector named x with length 10, where each value is a random numeric variable, or random numeric value. Okay, 2, use a loop and matrix indexing. I guess here it's just vector indexing. I was working on this while helping my child play alphabet bingo on a call with her kindergarten teacher. So use a loop and vector indexing to create a new vector called y, where each value yi is equal to 2xi. Okay, so first, we want to set up a vector named x with length 10, where each value is a random numeric variable. Anyone want to talk to me about what we could do for that?
So you would do for I in 1.
We're not at looping yet. But
Okay.
we could loop this, right?
Okay.
So let's kind of talk me through that.
So like what we did prior.
Yeah, sure. So why don't I make, let's call this sample space,
Mm-hmm.
and sample space will be equal to 1 to 10.
Mm-hmm.
Okay, so let's look at what sample space is going to be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's make x a vector with length equals 10. Right now we're going to make it a vector of just missing values with length of 10.
Mm-hmm.
Right? So we're going to initiate an empty object. In most other programming languages, you will often have to do this explicitly before we create something. We'll have to initiate something and then fill it. I'm going to show you why R is so awesome for doing statistical work after this. But if we were working in a lot of other programming languages, this is actually how we would have to populate lots of different things.
Huh.
Okay, so Anthony's suggestion is to basically loop, right? So we could do for I in 1, 2, and here I'm going to get clever. So maybe I know it's 10 right now, but let's say I want to have each of these integers sampled, right? So I'm going to use length sample space. I can use functions to set my beginning and end points for my loop. This is a really common notation, right? A really common, I don't know, way to a technique for handling things. For example, if I wanted to loop over every element of a list or every row in a data frame, I could do 1 to in row of the object I'm looping over, or 1 to length of the object I'm looping over, right? This is a really common way to do things. It's also really common to need to initialize empty objects, right? But actually, in this case, I'm going to do 1 to length x, because x is the vector I'm going to populate, and I want to make sure each element of that vector gets a value.
And do you want to do length of x then the length of sample space?
No, well, sample space is just where I'm going to sample random numbers from. And x is the thing I'm going to populate. So I want it to make sure to go in sequence through x, right? Now,
but shouldn't sample space be the same dimension as x?
No,
or x
that doesn't
same
matter,
as...
Oren. No, it doesn't matter. Sample space can be here. I'm gonna just to make this clearer. I'm gonna make sample space 1 to 3. It does not need to be the same dimensions, and I'll show you why in a moment. I haven't explained what I'm doing with sample space yet. Okay, so here we go. For x, so I'm going to show you 2 ways to do this. This is the first, where we're going to define x as a vector in A with length 10. In R, to define vectors or matrices, we need to give them, or data frames, we need to give them exact dimensions, right? So I'm going to show you this way to do it with exact dimensions. And in a second, I'm going to show you a flexible way to do it where I don't need to give exact dimensions. So now I'm going to sample I'm going to sample x, I'm going to sample one value from sample space, right? And let's see just what that does if you haven't used the sample function before. 1, 1, 1, 1, 1, 1. Hey, come on, give me something other than 1. Oh, right. I put it backwards. I sample from sample space 1 time. Is that right? Help functions are useful. Yeah, sample from x, size equals 1. Okay. I'm going to sample one value from sample space. 3, 1, 2, 3, 2, 3, right? It's drawing one random number from sample space. So now we're going to have, what we're going to get is a set of 10 random samples from, make yourself 0. It doesn't want to be. That's fine. Oh, why is this not working? Vector, make a vector of mode 0. Fine. I never work directly with vectors. So I'm going to just make 10 zeros. That's fine. That's the same thing, right? It's a numeric vector. Okay. Oops, but I didn't print anything and I didn't store anything. Oh, goodness. Okay, so what I'm going to do is I'm going to say x bracket I is equal to a sample from sample space of size 1. Okay, now just so we can see what this is doing first, I'm just going to print it. And we'll see what this does. Hey, look, 10 samples, right? Okay, now I could do this. And now, when I pull up x, I have populated it where before it was 0. Now it's going to be 10 random digits between 1 and 3. If I want to make sure I get the same thing the first time I run my code every time, I can set a seed. I don't know how many of you have been using set seeds, but this will fix it so the random numbers, at least the first time we run it, will draw the same thing every time. I'll set my seed. I usually just use 1. Sometimes people will use, whatever, 27. It doesn't matter. It just basically tells your computer this is the seed to use for your random number generator. So it ensures that you'll get reproducible results. Okay.
Does R pull a new seed every single time you run it?
If I don't specify a seed manually, yes, it will use a random.
Okay.
Yeah. So if I want my results to exactly reproduce, I need to use a seed. If I don't care about that, then it doesn't matter. I can just let it be random. I usually don't bother, but if you're working on an academic analysis for a paper or something, you may want your results to come out exactly the same each time, so you don't have to revise. Usually your sampling variance won't matter that. Okay, cool. So that was kind of tedious, right? What if I just did sample 1 to 3, 10? Replace equals true. Cool. Same thing. So R by default vectorizes things, right? So a lot of other programming languages don't, but in this case, R is totally happy to work within vectors, right? But we're gonna kind of just play this out for a second so we get our head around loops. So any questions about how I'm gonna remove set seed because that might be confusing, about what this does? Any questions about how this works? Again, this is a really simple loop, but this indexing trick where I make I my looping index, and then I use it to index a vector, a list, or a matrix is really, really useful and common.
What's the there's probably a complete random number generator, correct? Like if I just wanted to just generate 10 random numbers, not from a sample space.
R has many random number generators.
Okay, that's fine.
Will give me 10 random numbers with mean 0, standard deviation 1, right? RNorm will we've been using random number generators a lot, right? RBinome will give me random numbers where I want 10 random numbers from a binomial trial with 5 trials and probability equal to 0.2, right? R has a boatload of random number generators. So, typically I wouldn't bother with this. Typically I would say xi is RNorm. Let's make it each one is 1 with mean of 2 and standard deviation of 10, right? And that's going to give me 1 draw from that normal distribution, right? And now x is that. So yeah, no, R has a boatload of random number generators. I usually don't need to bother with defining my sample space. I just did that because why not? Because we could use sample to do that. Now, here I defined x as an empty vector of length 10. What if I don't know how long my object is, or I want it to be able to be dynamic to work over lots of different lengths of objects? What I might want to do is create an empty list, right? Where here I'm going to say n is equal to 10 to define n outside. I'm going to make n my index now. And x is just going to be an empty list. So x now is a list with 10 indexes, right? But what a list, so usually R, right? If I have a data frame of length 1, I can't assign something to the second row if it only has 1 row, right? I'd have to bind rows or rbind to do that. But lists can expand dynamically. So it's a little more useful. This isn't the most computationally efficient thing to do if we've got like a million expected outputs. Then McElrath suggests, then you may want to just go ahead and define, I know it's going to be a million long, so let's make a matrix or a vector that's a million long. But this list way of working means that if so let's say I define n dynamically somehow, right? I let n be a variable that depends on something else, then my x list can kind of shift along with it. And then once I have that list, I can bind rows x. Oh, it has to have names. Let's see. I can unlist x. Yeah, to turn it into a vector. So if I run all this, then I get my numeric vector out, but I didn't have to specify precisely what was going into it, right? Which can be very convenient. You can so the options here are either you can specify the length of your output holder precisely beforehand, or you can just define it as an empty list and then transform it into whatever you need it to be after. Unlist works if you have vectors. If you have like a list of data frames, then you can use bind underscore rows from tidyverse, and that will take a list and flatten it into a single data frame. It'll smush it together. We'll show you an example of that in a sec. Okay, so set up a vector named x with length 10 where each value is a random numeric value. We did that. Great. Now, use a loop and vector indexing to create a new vector called y, where each value, yi, is equal to 2xi. So, I've heard from Anthony and Oren already. Who wants to be my volunteer to work through this? Someone who's cool with sharing their screen and working through this. Or would you rather I just do it? Okay, no.
I can try.
I said not Anthony or Oren, but I appreciate the offer. I want to open it up a little.
No, Frank, I think you should go for it.
Okay, Sadaf.
Okay.
As the senior SCJ person, I will defer to your wisdom. All right. So our task here is to create a new vector called y, where each value yi is equal to 2xi. Right. So let's do the same thing I did before. Make y a list. I just like to use this list format because it makes me not have to think too hard about what dimensions my resulting object are going to be, which sometimes makes my brain hurt because my brain hurts sometimes. Okay. So again, same format because I know the y is going to be the same length as x, right? So there's no reason I couldn't just say for I in 1, 2, length x, now that x is already fixed, right? And I could also just say, well, whatever. We'll do the list thing again, because why not? Makes me have to think less. So now, we want to make each element of y equal to 2 times xi, right? So how do we do that? Y sub I is equal to 2 times x sub I, right? So there's x. Oh, I didn't unlist y yet. Okay, so my x and y are going to be different every time because I'm not running a seed right now. X is there, and now y is 2 times x. Oops. I need to store that in something, don't I? Okay, x and y. Right? Now every element y sub I is equal to 2 times x sub I. So we used a loop to assign values to each element of a list called x that we then smushed into a vector. And then we did for a list called y, we multiplied each value x sub I times 2 and stored that in y sub I. Right? And then we get a vector y, where each one is 2 times x. Now, of course, I could just say y is 2 times x because we're in R and everything is vectorized, right? I don't actually need to go through this step. This is a rather silly thing to do in R, but it's a really common thing to do in other programming languages. Now, when it's simple math operations like this, then, applying multiplication across two vectors is really easy for R to do. Where this gets harder is in doing things like reading and writing files. And this is when I tend to find that I use loops most. So I want to show you an example where we're going to work through something like that. When I said, then tell me a much easier way to do this, right? The much easier way is X is R norm, 10 values with mean equals, I don't know, 327, and standard deviation equals 100, and Y is equal to 2 times X, right? So we could either use 15 lines of code to do this, or we could use 2 lines of code to do this. The results will be the same, right? And that's, yeah, again, this idea of vectorizing operations, where we're applying, because of the matrix algebra and the way that R understands matrix algebra, right? It knows that, X times Y, when it's not a matrix operation, will go element by element through each operation. As long as the two are the same length, R can do this no problem. Yep. But looping is often how, when I was, learning programming in high school and C, this is, how we would have to write these operations, is to write a loop over them, and this is how we would do it, right? Okay, cool. So we good? That's the basics of loops. A lot of courses start here, and I think that's wrong because in R we very rarely need these tools, but when we do, they're really handy. So now I'm going to switch over to this lab programming setup.r file for another exercise. Okay, so you should all have this if you were able to pull or fetch. Does anyone have it? Thumbs up if you've got it. Yeah, I see. Okay, cool. So we have this. That's great. Now what we're going to do, first let me talk you through this. I want you to just run this. So you can source, just click the source button to run it, or Command A, Command Enter, or Command Shift Enter, Command Shift Return to just source the file. If you're in the Intermediate Stats project, it's actually going to create a new directory in your lab folder called Data Test, and then it's going to store a bunch of files in it. It's going to create and store a bunch of files in it. And so this is the kind of thing a loop is really awesome for. So what I'm going to do is I'm going to pretend like we have 5 years of data on 10 teachers, right? And each of those teachers had 20 students in their class each year, and they had 20 students take a test. And so what we have here is a file for each teacher for each year with those 20 test scores, with an indicator for which teacher it was and an indicator for which year it was. So first, we're going to use this dir.create to create a new directory. I get a warning because I've already made this directory, but if you haven't, you'll get no warning, and it's just going to make a new directory, right? Confirm that you're in the Intermediate Stats project, or at least where your working directory is Intermediate Stats, right? Because it's going to put that wherever your root folder is at that point, but that's fine. Now, we're going to loop over 5 years, right? And I'm going to say I have 13 teachers. So for those 13 teachers, I'm going to make a temporary data frame with class equal to I, year equal to year, right? I is my index here for teacher, year is my index for year. And then I'm going to draw test scores where I want each teacher to be a little different. So what I'm going to do is I'm going to draw 20 random values with a mean of 75 plus some random normal noise, right? So their mean is 75, but then each teacher gets a bump that's determined by a draw from this normal distribution. So this teacher is going to get a bump of 4 points. So their mean score is going to be 79. The next teacher, their bump is going to be 6 points, right? So this is just going to give us some pattern to the data where each teacher is basically going to be higher or lower. And we could think of this as like some kind of proxy for teacher quality or something, right? Or just variance in the composition of classrooms, who knows? And then, so the mean of this normal is 75 plus some noise, and then the standard deviation is always going to be 5. Now, I'm going to take this kind of long, crazy thing, the paste function can be really nice when I'm trying to output files. So let's see what this gives us. Let's say year is 1 and I is 3. So this function is going to give us that, which, hey, that's a file path, right? So what I did is I said the first part is ./lab/data-test, which is the folder I just created, /test. So I said whatever our working directory is, start there, go into the lab folder, go into the data test folder, and then test is going to be the beginning of my file name, comma, then put my value of year. In this case, that's 1. Test, so you can see here, test 1. Then put an underscore. Then put I in this case is 3. Then put .csv. And the important thing here is to put my separator between all of these strings is a blank, is nothing, right? I don't want them to be spaced out. Now, what would happen if I made it sep? The default is, if I remove this, the default is to put a space, right? And that is not good for a path, right? That's not good for a file name. So here, I want to make sure, I could also do sep equals bananas. And then it's going to be bananas, right? So in this case, sometimes you want a comma, sometimes you want different things, but sep equals blank with no space is really key for using it in this way. What paste does is it takes whatever vector of strings I have in here and smushes them together. So I should like paste alpha, gamma, party time, no, alpha, gamma, helicopter. It sounds like I'm in a frat doing that. And I'm like, no, but I just mean math. Then I get alpha, gamma, helicopter, right? Okay, so cool on how paste works. It's a function that you usually use for something like this. Yeah.
You said this was, I'm trying to find this folder. This is in the lab in intermediate statistics.
Correct. There's a file called lab programming setup. Does anyone have it open? Okay, cool. So it's up.
Okay.
Yeah, you just need to fetch or pull, but it's in your lab folder, lab directory, lab programming setup. This data test folder, the script is going to create that folder for you, as long as you're in the right root directory, which you will be if you're in the intermediate stats project. Right up here. Any other questions on the setup for this? Okay, so this is kind of crazy, and this is going to feel like, I don't know, for me, I feel like this is kind of like, whoa, I'm doing something neat when I do something like this. It's kind of power in terms of restructuring files on your computer and putting stuff in there. So I created a folder, and then I'm going to create 13 times 5 files in that folder, right? So we're going to end up with 65 files in that folder, each of which is a teacher's set of test scores for a given year, right? So 13 teachers over 5 years. So let's run this. Now, has anyone been able to successfully run the file? Run this? You have? No? Okay, so tell me if you get an error or anything. But if anyone has successfully done it, then I feel better.
I did not get an error.
Okay, cool. So what you should be able to do, in my case, I'm on a Mac, so I'm going to go to my Finder, Teaching, Intermediate Stats, Lab, Data Test. Remember, I just created that here, dir.create, made this directory, and then look at all these files I made, right? So this is something that is really common when we're going out and like grabbing data from somewhere or from the internet, or we're transforming data in some way and then outputting things in a new organized way. This is a really common practice to write things out in a structured way. And loops are awesome for that. Loops are totally awesome for that. But this is not actually what I wanted you to focus on. Right? I just wanted to walk you through how I set this up. The challenge for us now is to take this structured format. What we have here, right, is a really highly structured kind of system of file names, right? Where the first index here is the year, and the second index here is the teacher number. And we've got 65 of them. They're all laid out exactly the same. This is a really common way for data to be structured. Let's say I'm downloading 5 years of the Uniform Crime Reports, right? They're going to have consistent file structures. They're going to have consistent file names. I can put them all in the same directory called UCR data, and then I can write a loop to read over each of them, right? If they have a consistent format. So let's show you how to do that. Again, this is the kind of scenario that I use all the time for batch processing data, for batch processing output and for batch processing input, right? You could also do weird things like loop over ggplot parameters. So if you wanted to make like a plot of each, like a scatter plot of each variable against every other variable in a data set, and you had like 100 variables, right? You could do something like this and then write those all out as files for you to check out later, right? That's kind of a weird application because you could facet it and do it easier that way, but you get the idea. So it's a really flexible and powerful tool, especially for file processing. Okay, so
Frank,
Yeah.
sorry to interrupt you. I'm a little late to the game because I was trying to get it to work, and I finally got it to work, and it's really cool. But why would we need to do this?
excellent question.
Okay.
So let's say that I was scraping data of prison rosters from the web, right? Prisons often post daily inmate lists, right? And let's say those are usually not posted in a very machine readable format, but they are often posted, right? So I've written a web scraper in R and a scheduler to basically go online once every day at 9 in the morning, go to this website, parse their file, put it into a data frame that R can work with, and then write a file out of it. And so I had my computer automatically going online every day at 9, going to this website, downloading the file, turning it into something R could use, and then putting that CSV in a particular place, right? And so what that'll do is it'll give me a concrete file structure. Now, in that case, I was doing one a day, but let's say I'm doing some sort of fixed cleaning operation. Let's say I get the UCR data and it's messy as hell, right? So I want to load each of them in, and then I want to clean them, but I only want to have to do this once because it's really time intensive in terms of the computer time to do it. Then I'm going to write them all out as a new cleaned file, right? So I could do something like that. Where it's more common is in reading. You're right that the writing files is less common, but the reading files is super common. So let's work through how to do that.
Okay.
Does that kind of cover like
It does,
with
yeah.
the help
It makes
I
it a
actually
little
use
bit
this?
clearer.
Yeah. It's a little bit of a bizarre case, but I mean, I'm setting up an example now. So for example, Professor Rengifo and I are working on a new project where we are replicating some of my work on police killings using Brazilian data. And so we have now census data on each of the Brazilian states, and we have police killings data from each of the Brazilian states. But these are state level data, right? So what I need to do is to read through each of these in sequence, harmonize their structure, and merge them together, right? Now I could do that by hand. And in this case, it's only 16, 20 states. I should know that by now, but I don't off the top of my head. But if it were hundreds, right, that would be incredibly tedious. If the structure was similar enough, I could do this over a loop so that I didn't have to manually go through these spreadsheets and do it by hand. The other reason to do it this way instead of doing it by hand is that it's reproducible, right? Whatever edits I make to an Excel spreadsheet, like I could easily do something wrong and it's not reproducible because there's not, code that executes exactly the same way every time. There's lots of reasons. If I have to do batch processing of anything, the best way to do it is with code, and loops are a really helpful way to do that. But batch processing is kind of, the use case that I'm talking about here, where either we need to make a set of something that has the exact same format, or we need to read a set of something that has the exact same format, or similar enough format. So now that we've outputted this, let's input it. Okay, let's read it in. So we sourced lab programming setup. Now we're going to write a script to read in each of those files. Pretending that I don't know what those file names are, let's say that I just got this from some Department of Education website that had test scores for this group. I have no idea how many teachers and how many test scores are in here. Okay, so let's just kind of put on the veil of ignorance and pretend like we don't know what's going on. So I'm going to create a new R script. I'll just do this over in Scratch. Okay, so Scratch is just what I call places where I'm writing code that is just for kind of seeing how things work, kind of a sandbox. Okay, so I really like to use the tidyverse, so I'm going to tidyverse first. Okay, now, has anyone ever used list.files before? So, but we have used maybe ls over here, right? And I'm sorry, I put a parenthesis on it. ls in a Unix-like environment will give us the file directory, right? It'll give us the everything that's in that file, in the directory we're currently in, whatever path we're currently in. So, in this case, what I want to do is I want to go out and figure out, okay, what's in this data directory, and I want to get a vector that is a list of all the file names in that directory. So, in this case, actually, so Daf, do you mind if I kind of pivot for 1 second to actually show you something super nerdy that I'm working on that's a test case of exactly what I'm talking about? And everyone else kind of bear with me. You raised a interesting question. So I'm actually running something right now that has to do this. I'm running an imputation script of a large administrative data set. It's got about 5 million observations each year, right? And so I need to do, and I have 17 years of data, right? And so I have about 5 million rows and over 100 variables, right? So these are, individually, I believe 8 or 9 gigabyte data files. Now, if I tried to read them all at once and process them all at once, I don't have enough RAM allocated on, and R actually starts to bug out if it works with over 100 gigabytes of anything. But what I can do here, and I'll show you, this is the format we're going to use to run a loop, but this is exactly the kind of thing that I'm going to show you in a moment, where I'm going to loop over each of these files, apply some consistent set of transformations to each of those tables, select out the variables I want, right? And then do that in sequence to kind of shrink down the file sizes to just what I need. And this can get really handy there. The other place where I loop over file output is in the output of this, because what I'm doing is I'm doing multiple imputations. And we'll come to this, but what that's going to do is it's going to take the original data file and then stack however many imputations I'm running on top of it. So I take the original file size and in this case multiply it by 8, right? Because I'm creating 8 new data sets, or 8 plus 1, because I want to keep the original data. So in this impute incans, which is the file I'm using, I do use a loop to go over each year of the data, run the imputation model, and then output it into data file that I use that paste syntax to do it with. So this is actually something I use all the time. It may not be as useful to you, but this is the use case that I find myself kind of working through often. Okay, all that was an aside. So let's read this. So first we're going to use list.files. Now list.files, cool little function that does what it says. These functions produce a character vector of the names of files or directories in the named directory. I want to say file names is going to be a new object. It's going to be list.files. And I know that we put all this stuff in, where are you? Data analysis, no, teaching, intermediate stats, lab, data test, right? So list.files. And I know I'm already in intermediate stats, so it's lab/data test. Okay, so that's going to give me a vector that's equal to the length of the number of files in that directory. And it's going to have every single file listed as an element of that vector. Now, once I have this, if I want to get really clever and I want to say, okay, this is my big data folder, but I only want the UCR. And the UCR is in there along with maybe the American Community Survey or some other census product, and I only want the UCR. Then I could use things like grep or grepl to index that and search for particular file names, right? So I could say, okay, now take file names and only give me, let's say, year 5 will be file names, bracket. I guess I think I can filter a vector. Filter grepl test 5. Yeah, we can't. Because this is a vector, that won't work, but that's okay. We'll do it with a bracket. grepl file names test 5. Actually, I think I just want grep, so I want the indexes. All right. Look for test 5 in file names. Yeah. Okay, so now I only have those 5th-year tests. Right, so if there's a pattern to the names of my files, I can use tricks like regex searches or string searches to pull out particular subsets of this list of files, right? And that can get really handy. So let's start with the basics, though. Here's our file names, right? There we go. Now, in this case, I am going in. Now I could do length file names to get the length of my vector, but because these are data frames, right? So each of these is a file that has 3 columns and 20 rows, right? So trying to figure out exactly the dimensions of whatever my final object is going to be kind of tricky, right? So I'd rather just use a list, and I'm going to call it dat_in is a list, and just initiate an empty list. And the plan here is initiate an empty list, read each of these files in, and put it at index at each one at an index of the list. So then we're going to have a list where each element of the list is a data frame that is read in from that file. Yeah. So we're going to do for I in 1, 2 length of file names. We could also do, I think we could just do for I in file names. This isn't the format I typically use because it doesn't actually save that much time, but you can do it. So instead of saying for I in 1 to the length of file names, just iterate over each element of file names. I'm going to just show you the way I do it because I think it's a little less prone to user error. At least if I'm the user, it's a little less prone to error. But you could just iterate over the vector without specifying a start point. But in this case, 1 to length file names is going to give me 1, 2, 3, 1 through 65. Okay? And that's what I want. So now let's say dat_in bracket I to say element I. If we're doing list indexing, we use the double bracket, right? So element I of dat_in is going to be read CSV file names bracket I, right? So when I is 2, file names bracket I is going to be the second element of file names. Right? When I is 4, file names I will be the 4th element, right? So it's going to iterate through each element of the file names vector and then go grab those file names. Oh, but I have a problem here, right? I'm not currently in the file names directory, right? I'm in intermediate stats. I'm not even in lab, and I'm not in test data. So I could do 2 things here. I could set wd /lab/data test, and then this will work fine. Or I could set a variable called path, right? Where path is just going to be this, wherever those files live. And this is typically how I'll do it. So the path is just the folder that the files live in. And then I'm going to create a new variable called file name. We'll call it name temp, so we don't get confused with our file names vector. I use temp just to indicate things that are happening inside loops or functions so that I don't get confused with global variables. Now name temp is going to be equal to paste path file names I sep equals blank, right? So now when I is equal to 1, name temp, path wasn't defined yet. Name temp will be the direct path to that file. Okay, so let's just run this all and see what we get. Oh, right. I didn't update this. Now I just give it name temp as the path to the file. Okay. Got some warnings. I don't know what those are about, but oh, because it wrote out column names. That's fine. I guess we'll just forgot to. If you're ever using write.csv, make sure to say row.names equals false. I'm just going to run this again so I don't get that. Because otherwise it'll give you an empty vector called x1 that's just row names, and we don't really often need that. Okay, so what is in dat_in? That's the first element of dat_in, right? Is that teacher's test scores. That's the second element, right? That's the third, right? And this is the 65th, right? So each element now of dat_in is the read contents of that file. Now we have a 65 length list, each of those files, which then I can say test data is bind rows dat_in. And what bind rows is going to do, as long as everything in this list has the same column names, it's going to just smush them all together and give me one data frame out instead of 65 data frames out. So as long as the column structure is identical, this is fine. If it's not, then you can't do it this way. We need to be a little more creative. But now, test data has, instead of 20 rows, has 1,300 rows. Okay? We can see down here, right? I really want to look at it. Boom. Now I've taken those 65 files and smushed them all together into one giant object. Okay, that's the end of my unit on loops, right? I've kind of shown you how to batch output data, batch input data. We could, within this, if we really wanted to, we could then do transformations to this. We could say dat_in is equal to dat_in, but let's say I want to mutate test score transform equals test scores times 20, right? And then now my test data will have that transformation applied because I did it within the loop, right? I could rename variables. I could do whatever I want to within that loop, and then it'll apply it independently to each element, put it in the list, and then I can pull it out. I could also do that after it's out. But if I had differing file names, I may want to do things like case whens within here to make sure to harmonize everything. Right? Okay, so that was a lot, and this is a big, heavy topic, but I wanted to show you how this stuff works in case it comes up.
Right. So this works with. Does it have to be a read .csv file, or because I had one particular experience last year where I had to copy over like 3,453 pretrial reports, and literally it was like copy and paste, and I thought this is the stupidest thing ever. And
yeah,
basically it was like on a government website thing, and I thought there's got to be a way to do it.
This is an example of the kind of tools that I would use to solve that problem. Okay. No, you're right. You're right. I mean, any kind of monotonous task where you're doing the exact same thing over and over and over again, you should now start to think, how can I program this?
Try doing 3 years of daily meteorological data that way, copy and paste.
Yeah. So the other problem from a kind of science standpoint with copy and paste and manual input is it's super easy to make mistakes and super hard to find them, right?
Yeah, and that's why like it took 3 times as long because I had to like go back on every file and verify to try and catch errors.
Right, which if we could just write a script to go grab that data from the web and then process it in whatever way it needs to be processed and output it in whatever file format we need to output it, we've saved ourselves a lot of time, and we've guaranteed that whatever errors are produced as a result of us doing that are easily fixed, because we can see precisely in the code where it happened, rather than it being a result of, oops, I double pasted that one file and didn't realize it, or oops, I renamed that column incorrectly, or whatever. Right?
Yeah, that's half the reason I wanted to take this class.
I'm glad. And we're not getting like too far in the weeds on the programming applications, but this is the kind of stuff that you can do, and it's super powerful. So all that said, I'm going to quickly pivot over to functions because we've spent about 10 minutes longer here than I hoped to. Okay.
I don't know why, but it looks like I copied your thing exactly, but it's giving me an error.
Well, I'll push this code up at the end of lab, but I do need to push on because we only
Okay, thank you.
I have a lot of content to get through. Okay, so functions. We're going to make a vector of 10 random integers between 1 and 10. And I'm going to use the rbinom function here to draw 10 integers from a binomial trial of 10 coin flips, each with a probability of 0.5. For each of these represents how many heads I got. First trial 4, second trial 4, 2, 4, 6, 4, 3, 5, 5, 3, 3, 3. Right? So this is just drawing random binomial numbers. We've seen this before. But so that's my x. Right? Now, I want to add 1 to each value and then divide by 2. So in R, what I can do is I can define functions. Now we've been using functions like crazy, right? Let's say this is x, right? So let's go ahead and define x here. Okay, it's going to be different just because I, didn't set a seed. But we've been doing things like taking the mean of x. That's a function, right? Mean is a function. We've been doing things like taking the sum of x. That's a function, right? But there's no reason I can't make my own functions, right? I can define any function I like, right? For example, how do I take the mean of something?
Sum and divide by n.
That's right. So I'm going to call it my mean function. I'm going to define it as a function, which R is going to turn orange because that's a special thing, right? It's actually a function to make functions, but let's not think too hard about that. Okay, so I'm going to define a function with a single parameter, and that parameter is going to be x. And then I'm going to say that the mean of x is equal to the sum of x divided by the length of x. And then I'm going to return x. In a function, I need to tell it what to send back, right? Because a function is going to take an input and send an output. So we need to know what we're going to bring in, and we specify that here with whatever arguments we're going to take in, what are the variables and arguments we're going to bring in.
You want to return x?
I want to return mean x. Okay, thanks for that catch. And then I want to output typically one thing, right? So that might be a data frame, it might be a vector, it might be a single value. In this case, I'm returning a single value. So I have to run it to store it. But now, if I look at my environment, I now have something called my mean function in my environment. And if I just type my mean function, it's going to give me the block of code that I just put in there. So now I have x, and let's run my mean function on x and see what happens. 5. Right? It took the sum of it and divided by the length of it, which is going to be obviously equal to what the mean function gives us. Right? Now this is dumb, right? This doesn't actually help us at all. But we could write a function, say, to add 1 to each value and then divide by 2. right? So let's say we want to take each value in a vector, add 1 to it, and then divide it by 2. Okay. So in this case, what I'm going to do, so I have x. It's going to take variable as its single argument, right? That's the thing it's bringing in. That's the input. It's going to create a new object called temp, where it's going to add 1 to variable. And then it's going to divide temp by 2, and it's going to return temp. So someone who's not Anthony or Oren, tell me what the first row of x is going to give back. The first element of x is going to give back when I run it through my first function. Boys, you're doing great. I just want to, make sure that we have other people jumping in the conversation. No one? What if I run my first function on 6, what am I going to get? It's going to take 6. 6 will be called variable. It's going to make temp, which is going to be variable plus 1. So it's going to become 7. Then it's going to take temp and divide it by 2. So it's going to take 7 over 2. So it's going to return 3.5, right? So let's just see this in practice. My first function, 6. Oh, I didn't actually store it yet. Needs to be in the environment before I can run it. Cool, right? My first function, 67. Right, I can do this over and over. So when I have repeated operations that I'm going to do, maybe within a loop, but it's something I'm going to do many, many times, I typically want to write a function to handle it because it's a lot easier than writing the same code over and over again. Right? So in this case, I can apply my first function, one at a time, or because R is vectorized, I can apply my first function over a vector, right? And so it'll run over each element of that vector and give me all of that, right? Now that's not particularly useful, but kind of neat. That's a math operation, though I could easily just do x plus 1 over 2, or rather x plus 1 over 2 and get the same output, right? Because R knows to do that over a vector. But this is a really simple case, right? We could get far more complex. So let's get more complex. This is the normal probability density function, right? Now this is something I definitely don't want to write over and over again. And yeah, is it programmed into R already? For sure. But we could do it again, and we could also program new density functions into R, right? So we're learning about how to use user-defined, how to use any likelihood we want to specify our regression models, right? Now let's say that there's some probability distribution that's not programmed into R, but that we have a really good reason to want to use for a model. Now we can program it ourselves by making the probability density function a user-defined function and sending it to Stan to use. So let's work through this. This is the normal PDF. So this is an application for functions that you're going to see relatively often and in kind of more advanced R. Okay. I'm going to kind of make sure I have the equation over there. So I'm going to call this my normal PDF is better than D norm. And it's going to be a function. Now, in this case, a normal PDF needs 3 arguments, right? It needs whatever x we're going to evaluate, right? Needs that little x there because we want to basically when we go to a PDF, a probability density function, we're asking how likely are we to observe this particular value of x given a normal distribution with what parameters do we need for a normal? We can define a normal with 2 parameters, mu and sigma, right? Get that, this is awkward with video and whatnot. So we need x, to evaluate, and we need a mu and sigma for the PDF to say, how likely is this value of x in a normal that has a mean mu and a standard deviation sigma? So here, my function needs 3 arguments. It needs x, mu, and sigma. Needs those 3 things to work. Okay, so how do I translate this big wonky equation into R? Right? It's actually pretty straightforward to do. So we're going to do density. Density is kind of a reserve function. We'll say it dense out is equal to, let's just start working through the equation, right? 1 over sigma times SQRT 2 times, is pi defined? Pi has to be defined. Yeah, cool. 2 times pi, making sure that's a constant that R knows. 2 times pi, so we have the square root of 2 times pi and sigma in our denominator here. So this is covered, and the 1 over is covered, right? So that's this fraction is now covered. So we're going to multiply that by e to the minus 0.5 times, in the numerator is going to be x minus mu over sigma, right? So we want to wrap that x minus mu in another set of parentheses over sigma, and then we want to square that and then exponentiate the whole thing. That's the normal probability density function, right? And yeah, R already has that in, but we can very easily take any probability density function and program it in, right? We just have to understand the math well enough to translate it into R code, which it actually isn't that easy to do, or isn't that hard to do. So now I have my normal PDF is better than dnorm defined. So let's evaluate how likely we are to observe an x. Let's say x is equal to 20 in a normal 0, 1, right? So of course I made my life really hard on myself, but R is going to help me by giving me a pop-up with functions that are defined in the environment. So we're going to say x equals 20, mu equals 0, sigma equals 1. Oh, I didn't return anything. It didn't do anything because it ran that code and then didn't know what to do after that. So I need to make sure to return. Okay, I'm going to switch back over. So now let's try that again. And that is basically 0, right? 5 times 10 to the minus 88 is basically 0. So if I have a mu of 0 and a sigma of 1, I'm practically never going to observe a 20. But I should probably be less cute and just I'm just going to call this my PDF. Making everything hard to read. My PDF. And let's say, and again, so with functions, right, I can either explicitly name everything, x equals 1, mu equals 0, sigma equals 1. Now that's not too bad, 0.24, right? That has a probability density of observing a 1 of 0.24. But I also don't need to name these if I give them in the exact order that the function expects them, right? And the function expects x first, mu second, sigma third. Right? That's going to give me the same thing. And the normal is symmetric, so that's going to be the same thing. A minus 2 has a lower probability. A 0 is the mean, so it has the highest probability. Let's change this to a 10 one, and that's going to be very close to 0, right? Okay, so that's pretty cool. Now I can run PDFs. I can obtain the probability density of whatever I want because I've defined the normal PDF. And if R didn't have this built in, I now have it built in. Yeah. But I could also run it over, let's say x is, I think I can just run it over a vector. 0, 2, 3. Yeah. Now I can obtain the probability density of 3 values by giving it a vector that I want to look at. So let's say x is equal to a sequence between minus 2 and 3, right? So x is that. So let's run my PDF over X with mean 0, standard deviation 1. And that is the normal probability density at each of those points, right? And if I plot that, then it's going to start to look a little like a normal, right? And let's say phi equals 0.01 and run it again. Wow, right? That's pretty cool. The power of functions, okay? Questions on that? I'm going to do one more function example. This is the kind of, if we think of a function as a mathematical function, right? R is great with that. We can do that, no problem. If for some reason, in the book they show you, and they show you the likelihood for the Bernoulli, the likelihood for the normal, the likelihood for the whatever. And back in the olden days, one might have had to program those likelihoods in as user-defined functions, and then apply, your that likelihood function to your data manually, right? Now, if you want to be really clever, you can do that, and that's nice. But there's all kinds of other cases where you're going to have to do mathematical transformations or computations on your data that are not built-in functions. The life table example where I'm estimating rates of police-involved killings, there is a lot of math that we have to do to the data to transform them into standardized expected rates of death, right? When we don't have annual mortality data at the levels we want. But I need to apply that over a bunch of different times. So I've made a big, ugly function to compute the life table given a standard format of data. Okay, so now, last thing, and this is a bit silly. So let's combine both examples. So let's say that each teacher in our example data was someone from Star Wars, but we've temporarily, labeled them with integers. So Tidyverse has a neat little demo file called Star Wars. So I'm sorry, data Star Wars. If you have Tidyverse libraried in, then you can see this, right? Where it has the name, the height, the mass, the hair color, the skin color, the eye color, the gender, and a bunch of other stuff about each, 13 characters from the Star Wars universe. The scarves aren't for wearing, they're for dancing. I don't know if you're hearing the argument that's happening in the living room right now about proper dance etiquette. Okay, so all we're going to work with is name, right? But remember, we have test data, right? And what we're going to do is we're going to assume that each class, these integers, map on. So 9 maps on to Biggs. So what we do have is Star Wars name, right? We actually have 85. Okay, well, we'll just take the first 13. That's fine. Okay, so functions for data cleaning. This is really, really common, right? So let's say that I have the sort of, we worked through this a little bit with cleaning the other day, but let's say that I get data with state abbreviations. But what I really want, so I have AL and AR and AK, but what I really want is Alabama, Alaska, and Arkansas, right? I can write a function to take a vector of state abbreviations and turn them into state names, or to take a vector of state names and turn them into state abbreviations, right? And if this is an operation I need to do over and over again, that's really useful. Or let's say I get a vector of integers that correspond to a code for a state. Then I can use a function to take that integer and map it onto the name. And that's exactly what we're going to do here. So let's take the first 13 names. Our names, it's going to be Star Wars string name. We had 13 teachers, so I'm just going to take 1 to 13. Okay. So those are the teachers. We can determine which ones might have been better or worse at performing on tests, and then we can actually look at whether Chewbacca was a better teacher than Leia Organa. Okay. Sorry, I'm having too much fun with this. Now, what we want to do is create a user-defined function. So now we know that 1 is Luke, 2 is C3PO, 3 is R2D2, 4 is Darth Vader, 5 is Leia, 6 is Uncle Owen, right? 7 is Aunt Beru, and so on. So we're gonna do map names as a function of x. Okay, because what we need to take in is let's just make it a function of the data frame, right? We'll call it a function of dat. So we're going to take in our entire data frame of teachers, and then we're going to map those on to these 13 names. Okay, so what we can do here is we can say dat equal to dat, and we can either do a case when and go through row by row. I'm trying to think, how could we do this in a way where we just take the integer index and map it on to, so I think if we transform our names into a factor, that's going to give us a corresponding integer value that will map on to, right, okay, so levels our names, right? It alphabetized it. That's okay, we'll let it be alphabetized. So we're going to say that dat string teacher. So we're gonna, okay, well, let's do this with a mutate. Dat mutate teacher name equals what's the name of my data again? Just trying to remember the structure here. So class is our variable for a teacher, right? So it's going to be equal to the index of our name. Well, I guess we didn't actually need to go through that. So we can just take, so it's going to be equal to our names bracket class. So what we're going to do, our name, so class can be 9, I think this will work. Inspiring a lot of confidence when I say things like, I think this will work. Okay. Huh, for some reason, oh, I filtered it. That's right. Something screwed up. Rerun this. So I noticed I actually just have the same data repeated over and over again. For some reason, I just read in the same file, and I suspect that I may have, oh, I'm overwriting dat in every time. I see. I didn't index dat in, so it's only got the last file repeated many times. So I screwed that up. That's okay. Simple to fix. Now we're good. I'm going to look at the head and tail just to confirm that it all worked, and it did. Okay. So let's say that dat, called dat, test data. So when I'm working in a function, right, there's a lot of different, so there's more advanced ways we can debug it, but often what I'll do is I know that within my function, I'm going to call my data frame dat. I'm going to go ahead and just, in my environment, make an object called dat so I can confirm that my function works. All right, so let's say, and let's make sure our names is defined. Okay. Now, if I look at dat, teacher 1 is Luke, right? And teacher 9, 7, 8, 9 is Biggs Darklighter. And there we go. So this assigned each value of the teacher name in the order it was to our numeric ID for teachers. So map names works. So now what I can do is, let's say I want to read in my files sequentially and then add the teacher name in as I read it, right? So what I can do is now combine the steps we went through earlier. Path is already defined. I'm going to take my loop to read in files. I've defined map names. I'm going to read in dat in. Now I'm going to apply transformations to it. Dat in is equal to dat in, but I'm going to map names on dat in. Now, if I'm in tidyverse, I can just pipe the function and then tell it to apply map names onto itself with the dot. So let's just test this with I equal to 1. Right, same thing with loops as with functions. I want to get inside of it and just confirm that it works before I run the whole thing. But now dat in should have the Star Wars names attached, right, to that first file, and it does. Let's just confirm that with file 15. I don't know what file 15 is, but there we go. That's Obi-Wan. Okay. Apparently Obi-Wan students did not perform very well, but that's okay. Now we're going to make dat in bracket I equal to dat in, right? Always make sure to store it. So what we've done, I'm showing you this tidyverse way to do it. This is the base R way to do it, right? Is we would just say dat in map names of dat in, right? And there's no reason I couldn't do it like this, where I just apply dat in to the read CSV function, right, and nest it. But I like to do one line per command typically. So there we go. And then let's bind all the rows together. So that was 50, read CSV commands in a row. Oh. Ooh. What happened there? Something funky went on.
Is it because you kept the base version of it? And
I don't know. Kind of work through debugging this. It's possible. Let's see. Okay, so map in or dat in1. Let's just see what dat in1 looks like. Sorry, y'all. Should have worked this out before. Okay. Oh, I didn't return anything with map names. That's why. No, but whatever. The point is that with enough debugging, I could get this to work. For some reason, it's not right now. Let's say I is 5. Debugging is a fun part of that appears to have worked. Oh, I didn't define the, okay. It's because I had funky stuff going on and I didn't initiate it as a new list. Whatever. We're just going to wash our hands and call it quits there because you don't actually want to watch me debug this. But the point is, we can then use our functions to take repeated operations we would do, put them inside loops, apply those over each element of a thing, right? Or we can, apply it later. But user-defined functions, super cool, super flexible. In the thing like where we did the string manipulation data cleaning examples a couple weeks ago, we could easily have taken something like this and turned it into a function, right? If we were going to use this block of code over multiple data sets, which we did in that case, we used it over fatal encounters and we used it over population, right? We could easily turn this into a function to make this transformation of our age variable. Or the cleaning operations here, right? If we were going to need to clean multiple files, we could take these age cleaning processes and turn them into a user-defined function. If we were going to do it more than a couple times, then that would be wise. So again, this is a very very quick introduction to this stuff, and obviously the level of debugging required, as you're even seeing, more or less anytime I write my own function, I spend a good amount of time debugging it just to make sure it gets working right. But the kind of pain up front that you put into that, then you can trust the thing will just work, right? As long as the structure of the data you're working with is similar or identical.
If we use the idea of like cleaning up the data and renaming the variables like we did for the fatal encounters, but we had several entries, so we're not doing just one file. Would you then have automated like finding the unique entries for particular things? For example, like we had different ways to enter. Even there was like typos for female and things like that. You would do all of those, and then write a function that will apply all of those in out of names and so on. Because you can count on every file having the same errors.
That's correct. So I might want to make an exhaustive list of possible errors, right? And then program that. Or I might want to make rules that say, I'm just going to assume that we only have 3 possible values for gender in the data. We'll say that, we'll have like male, female, trans, gender non-conforming or something. And then we can basically we could write out a program to say, which of these values do we think it's closest to, right? Does it have like FE in it at all? And if it does, then we're going to call that female. Does it have only 4 characters? Then we're going to call that male, right? Or does it have the letters TR in it? Then we're going to call it trans, right? I don't know exactly what the right, that's there's also some advanced techniques that you can use, like fuzzy string matching, where you could get approximate matches. So we could ask, these are the 3 possible values: male, female, trans, right? And then we can run that through a fuzzy match and see which one it's closest to based on some computations we can do in terms of which word a particular typo is closest to, right? Those aren't perfect, but they're nice ways to automate that kind of matching task. It gets messy, and so like I run into this problem when I try and match U.S. county names, right? Where there's 3,000 of them, and there's no way I'm going to individually match 3,000 U.S. county names. Or matching surnames when I'm using automated court data and I want to match across like prison records and court records, and they're not always the same, right? So you could we could assume dates of birth are exact, and then we could do matching kind of closest string to surnames and first names or something like that. But yeah, so you're right. The code I provided is not perfect because it doesn't anticipate encountering new typos, right?
No, I just wanted to know if like my way of thinking about was the right way to go, where you would then, exactly like you said, you will try and tackle, okay, I'm gonna match it to these categories.
Yes.
And then obviously you're gonna have to write a much more complex code.
Yeah. So any other questions on this stuff?
So do these functions only exist within your current environment? I'm sure there's probably a way to save it forever.
They only exist in your current environment, and no, you can't save them forever.
Okay.
But
like a package. That's what I was like thinking.
No, so you could write your own package and push it up to CRAN. That's hard, but it's doable, right? Okay. There are examples. If you Google how to write your own R package, you can totally do it. And then I can put it on GitHub, and so CRAN has. If you want to author a package for R, it has to go through a lot of validation steps on the distribution network. But you could write your own package and put it on GitHub and load it, right? But the other thing we could do, and this is often what I'll do, is let's say I want to use map names a lot, right? What I can do is I can make a new R script, and put that over there. I'm going to call it functions.r. Now I'm going to clear that off, right? And I'm going to source functions.r. I need to put it in lab, not in lab. Now, map names is loaded.
And I would need to like,
Hey, Oren,
so I would need
we-
to import
Oren,
function.r.
please, let's let other people stop for get in for a second, because we need to end in a moment, and I just want to make sure I cover any other questions. So I can basically put as many functions as I wish into an external file, and then source it in, and then those files are available for me. So if you have functions that you use repeatedly, it's a really good idea to just make a growing list of functions that you use, put them in a functions file, source it in, and then you can access them without copying and pasting them into each script. So that's sourcing in an external file is the easiest way to do that. I don't really want to cover packages, but it's doable. Any other questions? And Oren, I can circle back to you if no one else has questions. So let's give a moment. No? Okay, Oren. So feel free to disconnect everyone, and I'll see you all on Friday, if not before. Oren, what was your question?
Oh, it was just a quick one. So if I want to use source, then I would want to have that function file in each one of my projects so I can call on it from there.
Yeah, if it's in you can source in
It'll be easier.
script, and it'll run whatever's in that R script, and if it's just a function, it'll read it and load it into the environment.
So that's nice. So that source is easier, is a little quicker than generating a package, basically.
Yes, generating a package is complicated. Sourcing a file is simple.
All right, great.
Yep.
Thanks.
No problem. Okay, well, we'll see y'all next time, and
All right.
and yeah.
All right.